So thank you very much. Thank you very much for the presentation. Let me, of course, start by thanking ICBS for the invitation to come here and for awarding a prize to one of my works. This is well, a very welcome thing that supports mine and my collaborators' research. So I'm very happy for that. So today I would like to talk about this work that is from almost 10 years ago now, and has to do with non-equilibrium dynamics in isolated quantum many-body systems, or transport in closed systems. Okay, so the basic question that this work is about, that this line of research is about, is essentially to explain how equilibrium physics emerges in quantum many-body systems. In other words, we have two basic settings. So we have isolated quantum systems that are typically prepared in pure states and evolved unitarily in the way that Schrödinger set up. And then on the other hand, we have quantum systems in equilibrium that are, according to quantum mechanics, described by mixed states. And these mixed states are supported by putting the system in contact with some bath. And the question that I would like to consider is, how do we pass from one description, how do we pass from one description to the other? Okay, so the basic setting that I would like to consider, the basic setting that one can consider to study this problem is the one of a so-called quantum quench. The idea is very simple. We consider a quantum many-body system, we prepare it in some states. We can think about it preparing in the ground state, for example. And then we evolve it with a Hamiltonian of which this state is not an eigenstate. A very simple way to do that is we consider a quantum system, we cool it down to the ground state, and then we suddenly change a parameter of the Hamiltonian in a way that the state is not an eigenstate of the new Hamiltonian anymore. And then we generate in this way some highly non-trivial quantum many-body dynamics. Okay? So this question was already considered, in fact, in the very early days of quantum mechanics by John von Neumann, but a systematic study only started in the late 2000s. And before continuing, let me very briefly mention why is it so. So why so recently? Why did we started a systematic study so recently? Well, essentially, the explanation for that is that this question has now become something that is experimentally relevant. So up to 20 years ago, the easiest quantum many-body system that we could realize in real labs were electrons in solids. Okay? So these systems are typically naturally open because electrons are typically coupled to phonons, to impurities. Their dynamics is very fast, and they're very hard to tune, which means that realizing a protocol like the one I described before is essentially impossible. Okay? Instead, over the last 20 years, there has been this breakthrough in experimental techniques that allowed for the realization of so-called cold atomic systems, which are clouds of cold atoms that are constrained by optical lattices, and are a very good way to essentially engineer quantum many-body systems in the way we like. In particular, these systems have a very good isolation, so they can really be considered as closed or isolated quantum many-body systems. And the second point is that their dynamics is slow enough that makes us able to actually observe the full evolution of the system. And the third point is that they are very easy to tune. And so it's actually feasible, very feasible, to realize in the experiments a protocol like the one I described at the beginning. So when you prepare the system in some state and then you change the parameter of the Hamiltonian, this you can actually do explicitly in practice here. And because of that, combining these ingredients, you can in fact now really realize in experiments quantum quenches. So the one I'm reporting here is probably the most famous experiment on a quantum quench. If you saw any talk on the topic, you probably saw this picture already. This is a very famous experiment realized by the group of David Weiss, Penn State, in 2006. So it's now a very old work. It was a new development when it was at the beginning of my path. And the idea is that what they did in this experiment is that they prepared cloud-cold atoms in some optical trap that is of a harmonic shape. And then what they did was giving a pulse to this cloud such that, let's say, half of the cloud gets momentum p and the other half gets momentum minus p and starts to oscillate inside the trap. And what was observed was that these oscillations were going on for very, very long without being damped in any way. But of course, there are many other examples of experiments on quantum quenches now. It's really a routine to make quantum quenches in experiments. Okay, so now that we understood why there was this big delay between von Neumann and more recent studies, we can go on and start to ask some physical questions. And the two main questions that one can ask in this setting can be stated as follows. Well, the first one is just to clarify essentially what we mean by relaxation. How can relaxation emerge in a setting where we only have pure unitary dynamics? Okay, this is question one. And the second question is, assuming that some form of relaxation will actually emerge, can we develop a statistical mechanics description of this? So these, back in 2016, when the work was done, were the two main questions that people were studying in this setting. Now, in the following 10 years, things have changed, and now people are starting to study also what happens for in the non-equilibrium, the true non-equilibrium dynamics of these systems for finite times. But before 2016, how this happened was understood in detail only for translational invariant systems. So when both the Hamiltonian of the system and the state that we consider were essentially homogeneous. And well, the work that I'm going to describe was one that provided a framework to also study instead inhomogeneous situations. Okay, so let's very quickly go through these two questions and understand what the point is, let's say. So let's start from the first point. How can the system relax despite purely unitary evolution? Okay, so of course, that's not possible for a finite number of degrees of freedom, okay? Here I'm just sketching a very, very simple example of the first year quantum mechanics, let's say. So we can look at a very simple Hamiltonian that is really just one spin. So we are looking at a system of one spin. We prepare it in some initial state that is not an eigenstate of the Hamiltonian. We let it to evolve, and we get this time evolving state here. But whenever we compute observables, then here we see that there are some interference terms that are showing persistence oscillations, right? So if I look at the plot of these observables in time, I don't see any relaxation, I just see oscillations, okay? So certainly here we don't see any sort of relaxation. And the same idea will be true whenever I do this thing for a finite number of degrees of freedom. I will not see any relaxation. Instead, relaxation can emerge whenever I consider an infinite number of degrees of freedom. Okay, so now let me look at a slightly more complicated example. So let's look at a spin half chain, and we do the same trick, right? We prepare it in some state that is not an eigenstate of the Hamiltonian. We let it to evolve, and then we compute observables exactly as we did before. But now we do that by also taking the limit of infinitely many spins. Okay, so we had L spins in this plot here. We want to take L to infinity. What changes? Well, what changes is that if we now plot the behavior of observables, we see curves that are more like this. In particular, this is a Bessel function. And so we see really some relaxation at infinite times. This thing will approach a finite number, a well-defined number, in this case 0. And the reason why that happens is essentially that all these interference terms that we saw before will now interfere destructively with one another. And because I'm taking the limit of infinite system size, these energy differences here will get smaller and smaller, and all these destructive interference will lead to some sort of relaxation. That's the idea. Okay? Does it always happen for all observables? Clearly not, right? I can take some observables, like this one, that are basically off-diagonal projectors on the eigenstates of the Hamiltonian, which will do exactly like my one-body problem of before, right? No relation at all. It's just oscillating indefinitely. But the idea is that, for observables that are local in space, the mechanism that I described before will apply, because they will overlap with many, infinitely many in the limit eigenstates of the Hamiltonian. And therefore I can have this interference and I can have relaxation. Okay, so the simple picture then that we can have is that if we have a big many-body system and we are only interested in a subsystem A, then the subsystem A will reach a stationary state, a time-independent state, if I first take the limit of B being infinitely large, and then I take the limit of infinite time. And the simple sketch to understand that is, we say that in this limit, what happens is that the system acts as its own buff, right? The idea is that the information flows away from the subsystem A and doesn't ever come back, because the system B is infinitely large, okay? Okay, so this explains essentially how equilibrium can occur in this setup, and essentially the kind of equilibrium that can occur is local equilibrium, okay? Very natural. The second question is whether we can develop a statistical mechanical description of such an equilibrium state. So we understand that there is an equilibrium state. Can we describe it in some efficient way that does not involve solving the full dynamics? Yes, we can. And once again, we don't need to be very creative. The idea is pretty simple, and it's the setup that James gave us. So what we do is we just maximize the entropy subject to the constraints given by the conservation laws, right? Nothing fancy. So then we have our von Neumann entropy, we have our conservation laws, and we need to really maximize the entropy with the constraints of the conservation law. The subtle question in this setting is, what are the conservation laws that we should include, that we should consider? Because, of course, if I have a quantum system, I will always have a number of conservation laws that is as many as the states in the Hilbert space, right? As the dimension of the Hilbert space, because I can, of course, always construct the projectors on the eigenstates of the Hamiltonian, and they are always conserved. Right? Are those relevant, interesting for my physical problem? No, right? No. These are not going to be important for my local physics. And what people have shown is that the only conservation laws that are actually relevant for my problem to actually find a quantitative description of the stationary state are those that are local in space, which means that they can be written as sums of some local densities, like the Hamiltonian itself, okay? Now, this sounds relatively simple, stated like that. It's more complicated if you start looking at the details, because then you will get systems that have some conservation laws that are not localized in one point precisely, but have tails. And then the question is, how fast should the tail decay in order for the conservation law to actually matter? That's a complicated business. But the concept is very simple. We just want something that is local enough in space in order to constrain my local relaxation. Please. Yes. It, exactly. So that indeed, if I have a chaotic non-integrable Hamiltonian, usually I will not have these conservation laws. But things are slightly more subtle than that. So it's not obvious that if I give a random Hamiltonian to you, then you won't have some weird conservation law, maybe only one or some strange thing. But yes, in the expectation is that in general, if the Hamiltonian is chaotic, you only have the Hamiltonian as the conservation law of this sort. Okay, very good. And so, how do we proceed? Did I go back? Yes, I think I did. Okay. So, basically, I didn't go back. I had the same slide of before, but here I put this Gibbs state now. So what we said before is that if we consider this limit, so we consider the rest of the system to be infinitely large, and then we take the limit of infinite times for a fixed subsystem, then we can describe the state of the subsystem with a stationary state. And now we said, in fact, with this stationary state can be written in a nice natural Gibbs form, where what I need to do is to specify essentially the chemical potentials associated with each one of these conservation laws, right? So these betas in the equation there. Okay, and how do we fix these chemical potentials? Are they fitting parameters of any sort? No. These chemical potentials are fixed, and are fixed by the conservation of the conservation laws. Because if I now look at the continuity equation for the charge densities, and I remember that I'm considering a homogeneous setup, then I have that the charge density itself is conserved in time, okay? And so I can use that to impose the value of my chemical potential for all the chemical potential, okay? So I have these equations and I can find what the chemical potentials are. Okay, so here we go to the example of a non-integrable system. So for a non-integrable system, we expect to have only one conservation law, the Hamiltonian. So the state that we construct is indeed the good old Gibbs ensemble. And we can fix the temperature by imposing that the expectation value of the energy density on the initial state is the same as in the stationary state. And we will find our ensemble, no problem. There is, as we already heard from the question, there are many systems. It's not the case, and this is the example of integrable systems that are actually very hard to avoid whenever you restrict the geometry to 1D. Okay, so if you look at one-dimensional setups, it's actually harder to be non-integrable than to be integrable. And for example, the two most famous examples of integrable systems are the XXZ Heisenberg magnet, so the simplest possible model that we can have of an interacting magnet, and the Fermi-Hubbard model, that is the simplest possible example that we can have of a solid. Okay, very good. So for systems like that, the procedure can still be applied. I need to now, I will have in these systems a number of conservation laws that scales with the size of the system. When I say conservation laws, I mean conservation laws of the form we discussed before, right? Of these local conservation laws that scales with the size of the system, right? So infinitely many in the thermodynamic limit. But I can still do the same thing. I will construct my ensemble of before, which now is indeed involving this very complicated sum of conservation laws, and because of that has been dubbed generalized Gibbs. Okay? But we can do the same thing. We can, again, determine what are the chemical potentials with a little bit more work, because there are many more of them. And what we find is that if we look at the evolution of some observable, what we will see is that it will relax to a value eventually at large times. Of course, here I'm thinking about a local observable, an observable of my local subsystem. It will relax to some value which is not the Gibbs ensemble, it's far from the Gibbs ensemble, and it's given by this generalized Gibbs ensemble. What is what? It's just some constant, because we don't know exactly how it's, I mean, we know that it scales with L, but we don't know exactly the coefficient. Okay, all good. So the question is, what changes when the system is, well, the word disappeared here, interesting, but it's inhomogeneous, right? When now we don't have the initial state and the Hamiltonian to be transition invariant, but one of the two or both are inhomogeneous. So what changes in this description? Well, we will have our Gibbs ensemble or generalized Gibbs ensemble that now takes a similar form, but now the chemical potentials is natural to assume will depend on position and time, right? And the idea is that we expect, again, some sort of local equilibration. So locally, the state will look like a Gibbs ensemble, but then the state on the next cell will be a bit different. So there will be some sort of flow from one part of the system to the other that will change the value of the chemical potentials, right? And so we can expect that, indeed, this will not be anymore something exactly true in the infinite time limit, but it's some asymptotic statement now, this kind of equilibration. So we can expect that for very large systems, and at very large times, but not infinity, we will have a description in terms of some sort of stationary state or quasi-stationary state. And how do we fix these chemical potentials? Well, in principle, the idea is similar to the one before. We look at the continuity equation for the charge density, right? We take the expectation value of the operatorial continuity equation. So here, these are scalar equations. And then what we can do is, we'll write an equation of that, and both these quantities here are functionals of the chemical potentials. And so in principle, to determine these chemical potentials, one has to basically invert these relations and solve this differential equation to determine the state. That is generically impossible. It's too difficult to do. So how can we solve? Is there a better way to solve these equations here? That's the question. Is there a more efficient way to deal with this problem? And that is the question that we studied in this now old paper. These are my collaborators in the work. So these are pictures taken from the first talk I gave on this paper in 2016. And these are the most updated pictures I could find now. So some people remained very similar. Jacopo, I would say, is not so different. Maurizio grew a beard and got a better camera. Well, Mario had a very strange evolution. Okay, so let's briefly describe what we did there. So let me check how much time I have in fact. Okay, so to understand how to deal with this problem, let's look at a simplest possible setting, right? The minimal amount of inhomogeneity I can put. I will take my Hamiltonian to be still homogeneous, okay? And I will take my state to be almost homogeneous. So I will take it in two blocks, right? A left part that is homogeneous and a right part that is homogeneous, but they are different from each other. So we can think about it as quantum quench again, where, well, left and right part of the system are in different states, no problem in preparing something like that. We can even think about preparing the system in some equilibrium states that are different left and right. This is even easier. Okay, so we do that, we prepare a state like this, and we evolve it in time with a homogeneous, as I said, integrable Hamiltonian. Integrable because this will be the yeah. the hardest case to treat with the previous approach. Okay, and then we consider, once again, expectation values of local observables at large times. And the two questions that we want to consider is, does this limit exist? So if I consider a local observable in this time evolving state and take t to infinity, do I find something meaningful? And can we compute this limit without solving explicit dynamics? Okay? Does the question make sense? Good? Right. So to understand what happens and to make some progress, let's start by looking at the simplest possible case, which is a non-interacting problem, okay? We want eventually to be able to solve interacting problems, those that I showed before, the examples of integrable models I showed a few slides ago are indeed interacting, but let's look at a free case first, okay? So let's look at the free Ferdinand even easier. And so we take a Hamiltonian that can be written as a sum of independent modes, and the occupation of each mode can be actually occupied or empty, so we can describe states, right, by giving a list of zeros and ones that are just telling us whether the specific mode is occupied or empty. And in the thermodynamic limit, this list becomes some sort of a smooth function. So the modes become dense, and I have some sort of a function that tells me, as a function of k, whether the mode k is occupied or not. So every stationary state in a free system is described by an occupation function like that. Okay? Very good. So what happens in a free system? In a free system, one can do an exact calculation, at least starting from Gaussian initial states. And the result that one finds is as follows. Sorry for the, there have been some issues with the conversion of these slides. So the first point is that the limit exists in the following sense. So if we take the limit of t to infinity of our observable of before, what we find is that it becomes the expectation value of the observable computed, for example, at position 0 in a homogeneous stationary state that depends on the ratio between x and t, which means that if I consider an observable at fixed position and infinite times, it will become a function of this ratio here being 0. But I can also consider observables whose distance from the junction, x is basically the distance from the junction here, scales with t, and then they will be described by different stationary states with respect to those that are spin. Okay? And the second point is that this stationary state, rho s of x over t, is characterized by the following mode occupation function. So, as I said before, all stationary states are described by a mode occupation function, and the mode occupation function describing this state is this one. It's basically a step function between modes of the left stationary state and modes of the right stationary state. And the interpretation is very simple, can be thought of in terms of propagating quasi-particles. Essentially, what we're saying is that if we look at modes that are moving faster, that are moving from left to right, so let's say that we are looking at this ray here, all the modes that are moving to the left faster than this ray will be the modes of the left system, and all those that are moving slower than the ray will be those of the right system. The other way around, sorry. The other way around. The ones that move faster than the ray will be the ones of the right system, and the other ones are those of the left system. But it's really just kinematics. Okay? Very good. But the solution of the free case is interesting because it also offers another important piece of information, which is that we can obtain this solution not only by solving exactly the problem, but also by making two observations without solving a problem. So, yes, which is key observation 1 here. So there are two steps that we want to make. The first one is we assume that such a stationary state for each ratio x over t exists. So we say that this limit is equal to the right-hand side for some state, rho stationary of x over t. And well, this state was characterized in a work essentially that was simultaneous a few months before the other one that I'm describing by Maurizio and I. Okay, and then we can characterize fully the stationary state by imposing the continuity equations. So if we take the continuity equations for all the charge densities, and then we take the infinite time limit, we find an equation that completely fixes our stationary state. So let me briefly go through how to do that. The idea is actually very simple. So whenever I have the expectation value of a charge density on some stationary state, since I have this interpretation of the free system in terms of modes, what I will have is basically I can write that as the integral of some function that depends on the conservation law, for example, the energy, times the occupation number, okay? It's really, I mean, I'm doing really, it's very, very simple kinetic theory here, nothing special. And the same can be written for the current, right? Also for the current, I have the same picture. It's just that now the function becomes essentially function times the derivative of the dispersion relation, which is the group velocity, okay? So it's the same thing. So then the point is that when I impose the equations that I wrote in the previous slide for all the conservation laws, then I can write them like this. And since they hold for all the conservation laws, they must be true for the integrand itself instead of for the integral. So I can get rid of the integral and I write some equation that involves only the occupation function, which gives me the solution that I wrote in the previous slide. Simple, nothing special. Okay, but then we have a very important second key observation, which makes us able to treat also interacting problems. The main observation is that in interacting integrable models, one still has this sort of description in terms of occupation functions. So generically, instead of having a single occupation function, one has a family of them, which can be thought of as having many different families of quasi-particles, okay? That's okay. But then we can write the expectation values of charges and currents in a very similar way as we did before. In particular, for charges, the expression is exactly the same as the one I wrote before, really exactly the same. Just here, I'm introducing this sum over the different species of quasi-particles. While for currents, well, finding the equation for the currents was essentially the main technical point of our work and of this other work that came out at the same time, and Takato will present in the afternoon. So finding this equation here for the current was the key. And you see, the equation for the current looks very similar to the one I wrote before. I just have to define what this V symbol here is. And what this V is really the same thing that we have in the free model. So it's the velocity of an excitation on top of a stationary state. But now this velocity is more complicated because of the interactions. So what happens here is that, so this is the velocity of elementary excitations over a stationary state. But because of the interactions, what happens is that if I have a state described by a certain number of quasi-particles, and I add another one, right? If I do it for a free system, nothing changes. I just put the red one in my state and nothing changes. But if I do it in an interacting problem, then all the other ones will also move, right? If I put one excitation, I make a kind of collective disturbance. And that's taken into account by this thing. So this equation, this velocity here is not just some independent function, is a solution. I have to kind of dress it with the interactions, and it will depend non-trivially on the density of quasi-particles. Okay? So if one wants to write explicitly what that means, one can write some integral equations. It's not very important to understand them in detail, but basically the point is that in an interacting problem, so where this kind of scattering matrix that I have here, scattering phase shift that I have here is non-trivial, then the velocity will fulfill some non-trivial equation and will depend non-trivially on the density of the quasi-particles I have. Okay? But once that is taken into account and put into this equation, well then we can write the final result exactly as we did for the free case. So we can write a simple kind of continuity-like equation, but in the scaling limit that we took. So this, we are considering again the limit of x over t fixed, taking both x and t to infinity. So this z here is x over t, is some sort of ray. Then we can write an equation that describes fully the state. And now let's look at what the predictions are. So if we look at this, if we think about a quench problem like the one I described before, let me start from the simplest possible one, which is when I prepare half of my system in some equilibrium state, some given state, and the other half in some different given states. Then we get profiles for example, the energy density or the energy current that looks like this. And we see this is a comparison between essentially what for us here is exact numerics. So it's ITBD simulations that are the symbols. And the lines that are exactly on top of these symbols are the predictions of the equation, the equation that I wrote before. Different lines here correspond to different parameters of the model. Notice that whenever this cosine of gamma here is non-zero, the model is non-trivially interacting. And you get essentially an exact description of this interacting problem. Something that you can also observe, and it's interesting from the physical point of view, is that in these systems here you will get indeed a non-zero current through the center of the system at infinite times. So you have that the stationary state that describes the area in the middle of the system is some sort of non-equilibrium steady state. Okay, you can repeat the same for different states. For example, I can take, I don't know, all spins up and all spins down. It works very similarly. Here I'm showing the magnetization profile and the magnetization current. Or you can do genuine quantum quenches where both states on the two sides are out of equilibrium. Okay. Also in this case, you find very good agreement. I mean, the agreement should be perfect at time infinity. I'm showing a result at time 15 for different observables now in this plot. But I mean, the message is that it works very well. Okay, you can go beyond the simple setting that I was describing. For example, instead of having now this kind of bipartitioning protocol where we have half of the system that is homogeneous and the other half that is different but also homogeneous, you can have some sort of general inhomogeneous initial profile. And then what happens is that the equation that we wrote before as a function of a single scaling variable, this x over t, needs to be broken up as a function of x and t separately. And as I was saying before, now we cannot really take the t to infinity limit explicitly because we will get some triviality. But this equation here will describe the asymptotic behavior for large but finite times. And you can, even this equation here that depends on x and t separately can be very efficiently solved numerically, as shown by many, many works. Here I'm reporting what I believe are the first ones that did it. And once again, one finds very good agreement with independent methods. Okay. Okay, so since then there have been quite a lot of development in these, and many different problems have been considered using this equation. Many different generalizations of this equation have been proposed to study, for example, different scaling regimes, so going beyond the ballistic scaling that I was considering there. But let me conclude very briefly by saying that this equation has since been used quite extensively to describe cold atom experiments. And the first work, I think, that provided a comprehensive discussion of that was this PRL from 2019 by Schemer, Bolschul, Dognon, and Dubail, where essentially they consider a quantum quench that is as follows. So they prepare the system in this kind of double well potential in an atom chip, something like that. So there are clouds of atoms in these two wells here, and then they release the system. So they just turn this potential off and let the system expand. So they look at the profile that does something like this, and they compare the experimental results with the predictions of these generalized hydrodynamics, as the equation of before has been called, of that equation. And well, the agreement is very good. And they showed in this paper that this actually gives the best available description. So they used other methods to describe this evolution. For example, conventional hydrodynamics, showing that conventional hydrodynamics after a while doesn't work anymore because it develops shocks and weird behaviors, which you don't have in the GHD equation, in the generalized hydrodynamics equation. Similar conclusions you can have been drawn in other experiments. This time, this work here by Malvania et al. In the group of David Weiss again, which instead considered a different setting. Instead of an atom chip, they considered an optical lattice, but the main conclusion, as I said, is similar. Recently, there have been also some recent works testing these even in solid-state systems. This, I found it relatively surprising. And in quantum computers, again, finding very good agreements. So let me essentially then conclude by giving a high-level summary of what I talked about, basically, which is that, so we started with this question. We were asking, how do we actually solve this equation here when we have now a very large number of equations, which we would need to essentially write down non-trivially and solve. And the idea is that you can solve these equations by making a change of variables. So you essentially change your variable, you describe your system not using the density of conservation laws, which would give you some very complicated description. But instead, if you have an integrable system, what is more convenient to do is to describe the system in terms of these densities of quasi-particles. This kind of momentum distribution of quasi-particle, which of course will depend on trivially on position and time, and you have some sort of evolution equation for this. Some kinetic equation for that allows you to describe the evolution of the system efficiently. And with that, I would like to conclude and to thank you for your attention.
Any questions?
Thank you for the nice talk. I have a question about implementation of the method. So does this require solving beta-ansatz equations iteratively? Because you mentioned that change in densities of quasi-particles impact these velocities. Well, yeah, how numerically expensive or how difficult is it to implement your equations?
Thank you very much for the question. Yeah, so the equations that so if you want to be precise technically, then the equations that you want to solve are those of thermodynamic methods, which are integral equations looking like these two, which you indeed solve iteratively, right? So you have an initial guess for your velocity and your distribution. You essentially implement it many times and try to find a fixed point. But that, if you just want to solve this is extremely efficient. In a few iterations, you just converge to the solution, no problem. Then, in fact, what might be a little bit more surprising is that it's also extremely efficient to solve this equation here, which is now more complicated because it's, you see, now this is a partial differential equation that depends separately on position and time. But you can still solve it very efficiently. There are, in fact, many methods. Maybe Takato will talk about them. But one efficient one is the method of characteristics you can use to solve this equation.
A follow-up question. So did I understand correctly that your index M is about the number of different types of quasi-particles you have in your model, and that for simple models, there would be only one quasi-particle type?
Yes and no. So you understood correctly, but depends on your definition of simple model. For example, if you think about the XXZ, well, in XXZ, there are many different types of quasi-particles that are different bound states of particles. All those will be different species. And in particular,
bound states.
Exactly. So precisely. So the interpretation is really that. So this M index describes the bound states, which in an integrable model are also perfectly legitimate stable quasi-particles that you need to describe.
Clear. Any other questions? Okay, so if not, so let's thank the speaker again.